All right, so part 2. So anyways, so it turns out that, again, here, what this turns out to be is this frequency ends up being the sum, or actually the average of the two frequencies between F1 and F2, and then the modulation here turns out to be controlled by the difference between these two frequencies. So you can actually show this using the trig identities that we did last time, and I'm not going to bother doing that. But it turns out that what we call the beat frequency is equal to the difference in the frequencies, which is equal to, in this case, F1 minus F2. I'm going to put the absolute value on those. So what we call the beat frequency then is simply equal to the difference in the frequencies, which in this case is equal to the difference of these two frequencies. So I'm not going to do an example of this yet. I will do one after we talk about the next topic, because I'm going to do an example of these two guys together. Once this thing allows me to actually sign in. So, would you stop? Trying to think I shouldn't have shut everything down. Whatever. So, let's do. So the next one we're going to talk about is, let's bring up my USI. So I can open it on here. So last thing we're going to talk about in this chapter is what's called the Doppler effect. So the Doppler effect is the apparent shift in frequency due to motion. So, bring up the Doppler effect. So, first video. The problem here is now nobody can actually hear this.
Here, if anybody gets it, I'm going as the Doppler effect.
You guys hear that?
No,
I think it's
I
an ad.
can demonstrate. Yeah. Terrific.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint.
Choo-choo train?
Close.
Brain damage choo-choo train?
Let's do another one. So what this one is it's going to be a guy playing a horn here, and he's playing at a constant note inside of the car. So this is what you're going to hear inside the car. So now they're going to switch from the car to somebody standing on the side of the road and see what difference you can hear. So this is the Doppler effect. So what the Doppler effect is, it is the apparent shift in frequency due to motion. So the Doppler effect is the apparent shift in frequency due to motion. So effectively, this thing can happen one of three ways. You saw one. So here, what this was demonstrating, what Sheldon was demonstrating as well, was the motion of the source. So one way that this can happen is that what? The source itself is moving. A second way that this can happen is that the observer is moving. So if the observer is moving, in that case, they'll also hear a different frequency due to the motion than of this observer. The third way is a combination of both of these. So this is basically both. So both the observer and the source are moving. So how does this work? So let me bring up kind of a quick simulation here. Okay. All right, I'll have to show you guys this on Monday or Wednesday. Why didn't you let me open? Well, anyways, so how this draws me. I hope you good. And I'll show you the actual simulation on Wednesday. So basically, what will happen is, let's take the first case. So let's look at scenario number 1. So scenario number 1, we have a moving source. So what will happen is, at some time, let's call this time 1, this thing's going to send out a spherical pulse. The spherical pulse is going to move some distance away, where this thing has moved a distance of the wavelength. Okay? But since this thing is moving, let's say it's moving to the right with the velocity of the source, this thing is at time 2 going to move to another location. So at some time later, let's say t2, this thing is going to be here, and again, it's going to send out another spherical pulse. So here's my spherical pulse, which again has moved only a distance of the wavelength. By the time this thing has moved, what happens then is that this spherical wavelength, though, has actually moved this distance outward. So this thing is actually going to move a sphere around here, where this thing has moved also by a distance of the wavelength. So what happens is, if I had an observer who was standing somewhere out here, what will happen is, since this wave here is moving at the speed of sound, so this red one here is moving outward at the speed of sound. This is speed sound. The blue one is also moving outward at the speed of sound. What will happen then is that as this wave is moving out, this first red wave, which has now gotten bigger, will first encounter then the observer. But the second wave pulse, which is the blue one, which is given out, will now encounter the observer much sooner than it should be if it was actually stationary. So what will happen then is the observer is going to think that this distance from here to here is actually the frequency, or the wavelength, between these two wave pulses. So basically, as this thing is moving to the right, the first wave is going to pass them. The second wave is going to pass them, but it's going to pass them at a much quicker interval, which means that the wavelength is going to be much shorter. However, on the other side, if I had an observer who is standing back here, what will happen on this side is this wave will pass them, but then the second pulse is now much further distance than what it should be, which means that this is going to have a different frequency, because it has a different wavelength. Let's call that lambda double prime. Right? So what happens is, as this wave is moving, the observer then is going to think that the frequency is much higher because the wavelength is much shorter. So as the source is moving towards him, because remember that velocity is equal to the wavelength times the frequency, that since he's encountering the frequencies much sooner, he's then going to think that the wavelength is much shorter, which forces then the frequency to increase. So he's going to hear a much higher frequency because of this apparent wavelength, because it's much smaller than it actually should be. This guy standing on this side, since he has this wave, but then the second one comes much later than what it should be, he's going to interpret that the wavelength is much greater. If I increase the wavelength, I then have to decrease the frequency, which means as it's moving away from him, the frequency then dips down. So he hears the apparent frequency then to be different. Now, we'll go through all the math on this next time, but let me show you case number 2, what happens there. So case number 2, I have a fixed source. This thing is not moving. So this thing is actually sending out wave pulses. Where each one of these is a fixed wavelength. By wavelength, wavelength, wavelength. Now in this case, if I take an observer who's walking here, who's then walking in the direction of, opposite the direction of the wave, so my observer is moving this way, while the speed of sound is moving this way, what'll happen is basically the same thing. So as this person is walking, he's going to encounter this wave, but as he keeps walking forward, he's going to encounter this wave at a much sooner rate than he should, because he's moving towards the wave. So if you think about something which is moving towards you, like a car, and you start walking towards the car, well, the speed of the car increases because you see it moving towards you faster because you're moving towards it. As opposed to if the same observer was now moving in this direction with the observer, he's now going to hear a lower pitch because now he's moving away, so the speed is now decreased, which means that the frequency in the wavelength is now different. So as I said, we'll go through all the math on this. I'll show you the simulation on Monday. I can't get the computer to come back on. But, or not Monday, Tuesday, Monday, Wednesday. So this will be the last topic in this chapter. So once we're done with this, we'll be all done. All right. So have a great holiday weekend, and I will see everybody middle of next week.